So number 5, what is the overall order? We have H2CO3 is the rate law given right here. You can imagine this is to the power of 1. And so to get the overall rate, 1 plus 3 is 4. There you go. Number 6. For 6, we use this usual formula. And so that would be 1 over 2. So you just plug it into this formula, and I would put a negative in front of both of these because they're both reactants. Dr. Spencer seems to leave the negative out right here. And then she gets a positive number, and then she just kind of puts the negative on here. And for that matter, it's I'm not sure why this wouldn't be negative, right? The rate with respect to hydrogen, it seems like that might be negative because it's a reactant. So you should ask Dr. Spencer if you're really worried about the sign. Number 7. If the concentration of hydrogen gas is doubled, so that would be looking at this rate law. I'll plug in some numbers to demonstrate. So we have rate equals K H2. So I'm going to invent a K because for figuring out if it doubles or quadruples or anything like that, it doesn't matter what K is. So this is rate. That's the general equation. And we'll invent a K, as I said. How about 1? And then H2 originally, we'll say it's originally 1 also. And we'll say the CO is 1. We'll just make everything 1. And you get 1. How interesting. So now when you double the H2, the K didn't change, my imaginary K. The H2 did change, so now it's 2 because it's doubled, and the CO didn't change. So you get 2. Hey, it doubled, which is what the answer is. Now, if I were to prove this works, if I were to change the carbon monoxide instead of the hydrogen, so everything starts at 1 as it did before. And now, instead of doubling the hydrogen, double the carbon monoxide. 2 to the power of 3 is 8. So it's, I don't think there's a good word for that. Octuples, I guess. It's times 8, which is what should happen since it's third order with respect to carbon monoxide. Now, obviously, if you needed an actual number and not just the fact that it doubles or whatever, then you would need the real K. But this is just for relative changes. For ratios, you can invent your own K. What is the delta G naught, I guess was pronounced like that, value at 25 degrees Celsius? Just plug it into the formula. Make sure to use Kelvin. What temperature values is it spontaneous? So this formula, well, the cutoff point is always the cutoff point for where it's spontaneous or not is always at G equals 0, delta G equals 0, as shown in this, and I'll post this link. So delta G is less than 0, spontaneous equals 0, not really sure, well, nothing happens. It's equilibrium, that is actually the better word. And greater than 0, not spontaneous. So if you set it equal to 0, then that's how you can figure out what the temperature, what the temperature where it changes between this category and this category is. So So if we take this famous formula and set delta G equal to 0, we have 0 equals delta HF. Well, I suppose it would be a formation if, depending on what you're working with, it might have the superscript 0 and subscript F. You'll have to ask Dr. Spencer when those show up or not. I believe the subscript 0. I'm not going to say for sure because I'm really not sure. But looks like based on this example, yeah, these are heats of formation. But entropy of formation, maybe? Definitely you'll have to look that up. Or I'll stick it at the end of this video. My point is the algebra more than the notation. So if we move the delta T, the T delta S over, then we have this, which we can solve for temperature. And I believe that's what Dr. Spencer did. Yes, she has T equals delta H over delta S, which I just showed you how you get that. I didn't really show the last step. You divide both sides and there you go. Delta H over delta S. I might have said delta F a second ago. So, there's that. Math happens. And as far as knowing the greater than or the less than, you just have to know this chart. Not that chart. This chart. This chart is the key.